Hi dear students, welcome to statistics class. This is our module 2, topic 3, measures of dispersion under descriptive measures. Last topic, we have talked about the measures of location or central tendency, and you've learned that it will give us a typical value of our data set. So today, we'll be learning and talking about the measures of dispersion. Why it's so important? Because we need to be able to understand how the degree to which data values are spread out in a distribution. And through these measures of dispersion, it will determine the nature and cause of variation. For example, you have a greater variability. And then when you look at your data set, why I have a mean like this? Why I have a greater variability? It is because of your outlier. Outlier means the extreme values. So through this, you'll be able to determine the cause of variations. And while central tendency tells you where most of your data lies or your data points lies, variability summarizes how far apart your points from each other. For example, in the mean, you will have a single value, but you don't know about the other data points. How far are they from the mean? So this variability or dispersion will give you an idea of how far apart from each other your points are in your data set. So let's define it. So a quantity that describes the spread or variability of the observations in a given data set. And remember that the higher the value, the greater the variability in the data set. And there are some common measures. We have the range, the interquartile range, the variance, the standard deviation, and the coefficient of variation. This coefficient of variation is really important in the experimental researches, especially for agriculture and biology. So these types of dispersion are also grouped. So there are absolute measures of dispersion, and under which are the range, the interquartile range, the variance, the standard deviation. And the relative measures of dispersion, we have the coefficient of variation, or we can call it as CV. So range. So let's define it. The difference between the maximum and the minimum values in a data set. Last topic, we've talked about what is the maximum value, what's the minimum value by their definition. So when you compute for the range, it's just the difference between the maximum and the minimum value. And the range is the difference between the largest and the smallest number in the set. Okay, so the range, there are some critics that the range is not a very useful measure of variation as it only uses two values of the data. Because, as I've said, you just have to take the maximum and the minimum value. But how about the data points in between them? How far are they from each other? So that's one of the critic in using the range. But still, it is useful, or it's still one of the measures of variation. So other measures of variation will that we'll be talking about later will be more useful as they are computed by using every data value. Unlike the range, we can only use the maximum and the minimum value. Okay, for example, the life expectancy in Human Development Index in the United Nations Human Development Report, and the man that lived the longest in the Bible. So the maximum value is Methuselah is 969 years old. And the minimum, or this is the life expectancy of today's time. We have 70 years old, the average lifespan or the life expectancy. So to compute for the range, we just have to subtract 969 minus 70. So that is the range 899. But we don't know how about the generations from the other time. So how far are they from, for example, from our life expectancy of today? So this range can only cater the maximum value and the minimum value without the idea of the values in between or the other values. Okay, so that's how you compute for the range. So it's just so easy. So let's proceed. So some properties of the range, it is quick and easy to understand because it will only use two values, the maximum and the minimum. And it is a rough measure of dispersion. It is usually reported together with the median for you to know the middle value. And before we proceed to variance, let's compute for the deviation from the mean. Let's define it first. The deviation from the word deviation from the mean. The mean that I'm talking about is the arithmetic mean that we have computed in the previous topic in the central tendency. So deviation, that means is the distance from or away from the mean. Okay, for example, you in your data values you have a mean of 85, and then in 85 the mean grade of your classmates, and then what is the deviation of student 1 to the mean? So that is the deviation from the mean. Then it's just like the range. However, you are using the mean and the observed value. So let's define it. So the deviation from the mean is found by subtracting the mean over a set of data from the given observation. For the finite population, x1, x2 until xn, the deviations are observed value, uh, first observed value minus the population mean, the second value minus the population mean, so on until our nth observation. So if we have the sample, then we can use the x bar instead of our population mean or the mu. So note that the sum of the deviations from the mean is 0 for any set of data, and that is the principle already. Now let's proceed to variance. The variance usually use this sigma squared. The small letter for this sigma shaped like this and then squared. So the average square difference of the observations from the mean. Last time, in the previous slide, we've talked about the deviation from the mean. So the variance, since it will always end up to 0, the deviation from the mean will always be 0. So to circumvent this problem, statisticians and mathematicians formulated this variance. So before they sum it or they add it up together, they square it first. The deviation, you can see here, it's like a deviation from the mean. And then one observation, and then minus or subtracted to the mean, and then squared it. So that becomes the variance divided by n. And then where xi is the ith observation in the data set, mu is the population mean of the data set, and n is the total number of observations in the data set, or n is the population size. So this is our second measure of second measure of dispersion, the variance. Okay, let's proceed. We have here the sample variance. Whenever you see this s squared, this would signify that my data came from a sample. Okay, it's just a sample variance. Whereas if you use the sigma, then that is the population variance. So this is the formula for our sample variance. S squared is equal to summation of xi minus x bar squared, where I ranges from 1 to n, over n minus 1. So remember or take note, this is our formula 2.3.2. That means it is for our module 2, topic 3, second formula. Okay, that is our notation. So that you will not easily forget it. Remember, this coding is module 2, topic 3, second formula. Okay, so where xi is equal to ith observation in the data set, and x bar is the sample mean of the data set, and n is the total sample number of observations in the data set, or the sample size. So that is our sample variance. Okay, what are some properties of the variance? So one of the most useful measures of dispersion, because every value or every data point has its own contribution to the value of your variance. So all observations contribute to the computations. And remember, it is always non-negative. So whenever you have an answer of negative in computing your variance, I tell you, check your computation again. So comes in the square of the unit of measure of the given set of values. Okay, for example, this is the area planted for durian by region in the Philippines last 2015 according to Philippine Statistics Authority. So I know that most of the CPAsians love durian, so I took this data. So let's compute for our population variance. Okay, let me read it from Car region. We have the 0. That means there is no durian in that area, and then only 1 hectare. Remember, this is in hectare unit. In region 1, 4 hectares. In region 2, 4 hectares. In region 3, 37 hectares. In region 4A, I think that's Calabar zone. And then Mimaropa region, 45 hectares. Region 5 or Bicol, there is no record. There's no durian in there. And then Western Visayas is 171 hectares. Central Visayas is 24 hectares. Region 8 is 32 hectares. Region 9 is 1,091 hectares. Region 10 is 1,423 hectares. Region 11 is 8,330. I think it's in Davao. So now you have an idea of what place there's a lot of area planted for durian. And then the region 12 is 2,202 hectares. Region 13 is 1,935, and BARMM, Bangsang Moro Administrative, something like that region, 1,314.75 hectares. So using this data, the total hectares is 16,613.75 hectares, or the area planted for durian in the Philippines. So using the same data, we have also the mean of 1,038.4. Okay, that is the mean, the average or the arithmetic mean for area planted. So how do we compute for population variance? Okay, this is our data. This is our formula. Remember this in our formula, module 2, topic 3, module 2, topic 3, formula 1 is our variance. The population variance is the summation of xi minus mu squared. We use the mu because we're talking about the national data, and then over the population size. Total, we have the population size of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's the number of regions in the Philippines, or 16 rather. And now to compute using this formula, xi, this is our first observation. It is 0. And then minus the population mean, 1038.4, and then squared. So where do we get that mean or the population mean? Here in our computation, 1038.4, and then open close parenthesis, square it, and then plus, since you can see here the summation notation or the principle that we've learned in the module 1, and then 1 because the region 1 is have only 1 hectare, minus our population mean, and then square, and then 4 because the region 2 is 4 hectares, minus subtract to our mean, then so on and so forth until we finish all the regions. So we can see there the ellipses. So until BARMM region. So divided by, because we have the sample size, or population size rather, we have the 16 regions in the Philippines. Okay, so computing it with your calculator or your Excel, you will arrive to this value. Okay, so that is 65,708,931.50 over 16. So our variance is like this. The value is 4108,06808.219. That is our variance. And if you square it, for the standard deviation, you just square it, which we will be learning after these slides, slides after this. And then, so I think that's how you just compute your variance. It's just so easy, right? Oh, this is our population standard deviation. Okay, so here's the third measure of dispersion. So standard deviation gives more clarity about the deviation of data from a mean. For example, whether a reporter is analyzing the high temperature forecasted for two different cities, a low standard deviation would show a reliable weather forecast. So this is important in your researches, in your, especially the experimental and as well as for social researches, to see the reliability. What's the use of learning something if it's not reliable after all? Even if you will introduce something, for example, the vaccine, if it's not reliable, there is inconsistency, so it's so dangerous. So that's why in experimental researches, it's important to tell or to project, to present the standard deviation. So let's proceed. Standard deviation, they use the sigma. Remember the population variance, you just put the square there. But if it's standard deviation, you just use the sigma. This is for population standard deviation, or SD to make it short, or S. Okay, so the average deviation of the observations from the mean. And then it is the positive square root of the variance, just like what we did in the previous slide. We just squared it, and I mean the square, or you get the square root of that. And then the unit measure is the same as that of the observations, because in standard deviations, you are squaring each value. But your original data is not squared. So to circumvent these issues, mathematicians and statisticians just employ this principle to get the square root, to bring it to the same unit measure, just like what we have in the original data or in our observation. And it is usually reported with the mean. the measures of variations of the scores about the mean. So why do we need this? Why not use the variance? Because the standard deviation, as I've said, it is unitless, and it makes much easier to work with and easy to interpret in conjunction with the concept of the normal curve. So the same units as the original values. That's why researchers, or if you are analyst, you can easily determine the variability of your data by just looking the standard deviation. The lower the standard deviation, the reliable, but the higher it is, it's not that reliable, but depending on your subject, on your discipline. Because for medicine, they really need to have a very minimal standard deviation. And there are tolerable, and then for some, they will accept the higher standard deviation depending on your subject. Okay, so recall our sample variance in our formula 2.3.2. S squared is equal to summation of xi minus x bar squared, where I ranges from 1 to n, over n minus 1. So why do we use this n minus 1? They call it as the degree of freedom. Okay, and then to get the square root, just transpose it to get the standard deviation. That would become our formula 2.3.3. And if you want to have a shortcut formula, if you're just using your calculator, you can use this square root of n. This is our sample size, open parentheses, summation of xi squared, meaning you square each values and then you sum it, then multiplied to n, minus the summation of xi, where I ranges from 1 to n. You sum every data values and then you square it, over n, or sample size, times n minus 1. And that becomes our formula 2.3.4. Okay, using the previous example, like the areas planted with durian in the Philippines, assuming that the data to be a random sample, we have here our formula 2.3.3. And then this is our standard deviation and this is our sample variance. So to compute for a sample variance, we have here 0, the same process, 0, since this is the value in the first region, and the mean, and then squared, so on until the bar region. And then for the sample variance, 16 minus 1. Okay, and then s squared, you sum it, you will arrive in this value divided by 15, and then you get the square root, and then you will have the standard deviation of 2092.9872. So during our online class, I will teach you how to use your scientific calculator. Okay, so using the shortcut formula with the same data in the previous example. So we have here the sample size, 16, and then summation of xi, you square it, summation of xi squared, 0 squared is 0, 1 squared is 1, 4 squared is 16, 4 squared is 16, 37 squared is 1,369, so on, all of the region. So the sum of that, before you square that first and then you sum it. That's why we substitute this value, this here, because it is the summation of xi. Here, this is our xi. Summation of xi squared minus the summation of xi. So the total 16,613 squared over 16 times 15. So in the end, we can get the value of 2,992. So it's the same as we have using the formula 2.2.3 in the previous slide. Okay, so these are the simple symbols for standard deviation. If you're talking about the sample, in some textbook, you can get the S, and then for population, the sigma, and some graphics calculator, they use the SX, and then some graphics calculator as well, the sigma X, and then some non-graphics calculator, they use the X, sigma, then subscript of n minus 1. N minus 1 is it signifies or represents the sample because in the denominator we have the n minus 1 as our degrees of freedom. And then x, sigma, n. So for articles in professional journals and reports often use standard deviations. For standard deviation, use SD. These are the shortcut, and var for variance. So now let's proceed to the fourth measure of dispersion, the coefficient of variation. The CV is really present in the experimental researches, especially for agriculture and biology. And so it is the relative measures that indicates the magnitude of variation relative to the magnitude of the mean expressed in percent denoted as CV. So you compute first your variance over the mean multiplied to 100. And this becomes our formula, Module 2, Topic 3, fifth formula. So remember this, coefficient of variation. So instead of saying coefficient of variation, to shorten it, I will just say CV, and I'm talking about the coefficient of variation. Okay, so some properties of CV, it is unitless as well, and it is used to compare dispersion of two or more datasets with the same or different units. So the higher the CV, the more variable is the data set relative to its mean. So for experimental researches, CV indicates the degree of precision with which the treatments are compared and is a good index of reliability of the experiment according to Gomez. I've given this textbook to you in our iLearn. So example, to compute your CV, such as sigma or population, standard deviation or sample standard deviation over our mean times or multiplied to 100. So using our previous formula, we have there our population variance of 2,206 divided by our mean times 100. So our CV, our coefficient of variation is 195. So remember, the higher the CV, the less reliable it is. But depending on your subject and the subject of your study. So before we end, let's remember this verse. Deuteronomy 7 verse 9. Therefore know that the Lord your God, He is God, the faithful God who keeps covenant and mercy for 1,000 generations with those who love and keep His commandments. Remember, our God is constant. He is not changing, and He is not deviating to His promises for us. So let's not also deviate our promise that we will be faithful as we are waiting for God's soon return. God bless you on your next topic.